All right, in part 3 of our labor supply online lesson, we're going to look at a concept called the reservation wage. And all the reservation wage is, it's the wage at which the worker will start working. So in microeconomics, the reservation price is the price at which a seller will consider parting with a good that they're selling. In eBay, when it was mostly auction or all auction, when you set up an auction for an item that you wanted to sell, you'd have to specify your reservation price. And if the price, if the bidders didn't exceed your reservation price, the item wasn't sold. So in order for the bidders to win the auction, they had to exceed your hidden reservation price. And the reservation wage is similar to that. In this situation here, we have an individual facing a trade-off between leisure and labor in a given week. The individual derives utility from both consumption and leisure. The worker collects a $583 payment each week in non-labor income, and we're assuming it comes from a rental property. The person earns $7.29 per hour with her present employer, and she can devote at most 80 hours a week to work at this employer or in leisure because of family constraints, sleep constraints, family constraints. So she budgets 80 hours a week for leisure and work. We're going to use this information to answer the questions, right? So let's go ahead and build her budget line. Her allowance, weekly allowance, is 583. Her wage is 7.29. Her total time allotted to work or leisure is 80. The intercept of her budget line is the allowance plus the wage rate per hour times her time constraint. And so her budget line is defined by C being consumption, the intercept B minus the hourly wage times the amount of leisure the person purchases. Okay, that's your budget constraint. All right, and then hours worked is going to be the difference between total time devoted that can be devoted to work or leisure minus leisure. And I probably need to put a box in here for leisure. Okay. And then utilities are given here on the indifference curves. Okay. So the worker's optimal solution is a point of tangency, right? This point here, of the 3 points, the green points, this point is affordable. The person is on the budget line. The person is not saving. The person is using all of their income, earned or not, for consumer goods. But this person could be happier if they generally consume more goods and services and leisure, right? Or slid down the budget line to this point here. So when this person slides down the budget line, they're getting less and less consumer goods and services and getting more leisure. And so the person has higher utility here, right? This person has higher utility here. Now, the person can't be on this indifference curve because no point on this indifference curve is affordable, because no point on this indifference curve touches the budget line. The budget is the combination of goods and services and leisure that she can afford, right? The area under the budget line would represent consumption bundles of consumer goods and services and leisure, such that she has savings. But we're going to assume she has no savings, right? She's not interested in savings. All right. So the optimal solution is this tangency point. At this tangency point, her leisure is 80. So we're going to put 80 here. We're going to put 80 here. Now, putting 80 there means her consumption is 583, which is completely reasonable because in the graph, when you go to the left here, it's under 600, right? So her consumption is 583. She's going to work 0 hours per week because, again, she only has 80 to devote to leisure or work, right? So if she's got 80 hours budgeted for work or leisure, and she chooses 80 hours of leisure, she is basically choosing not to work, right? And that results in a utility level of 216 because this utility equal 216, that's the value of utility all along this curve, right? So utility is 216. All right, now we want to find the consumption level. And I've already done this here, right? So this is the budget constraint. She can spend money on goods and services, and she can buy leisure, right? Each additional hour of leisure costs her an hour's wage, right? This is the value of her time, total time, and this is her allowance. Solving for L, right? Solving for L, we get this equation down here, which is what this is right here, right? These two are identical. Okay. Because my B is a 7.29 times 80 plus 583. That's this value right here, right? So this sum, which ends up being this value, right? You can see it right here. This is 1,166.2, right? Minus the 7.29, right? So this and that are the same thing. So at 80 hours of leisure, her consumption is 583, which makes sense, right? Because she has zero earnings. She has zero earnings because she has worked 0 hours. So 0 times her wage is 0. And so her consumption comes purely out of that weekly allowance she gets from the property she inherited from her parents, right? That's rental income she gets, right? Now, notice the slope on the indifference curve. Again, the slope on the indifference curve is non-constant. Here on the indifference curve here, leisure is relatively scarce. So the consumer or worker here is willing to give up a lot of consumption for a little more leisure, right? But down here at this point, the indifference curve is rather flat. And so when you drop down vertically and then go to the right to the curve, you get that person's getting a little bit more leisure, but it's not giving up very much consumption, right? As opposed to here, a huge drop in consumption to get a little more leisure, right? And that's because leisure is not scarce here and consumer goods are super abundant. Down here, leisure is not scarce, but consumer goods are scarce. And that's why this curve bows toward the origin, right? Now, the slope of the indifference curve is called the marginal rate of substitution, right? We've mentioned this quite a bit so far. It equals the slope of the budget line at the tangency point. At this point, the indifference curve intersects, that's the one point of intersection between this green line and this black line. There's only one point of intersection. And if you blow this up right here, if you zoom in right here, the green indifference curve will look like a line. It'll look like the budget line. So at this point, the curve and the black line are essentially parallel, which means they have the same slope, which means although the marginal rate of substitution is a lot higher here, right? A lot more negative here than it is here, meaning the slope of this curve varies over leisure. At this point, the slope or the marginal rate of substitution of the indifference curve equals the slope of the budget line. The slope of the budget line is called the economic rate of substitution, and it's equal to the wage rate, and it's constant. So the slope of the budget line equals negative 7.29. So the slope of the budget line equals 7.29. And the marginal rate of substitution, the slope of the indifference curve, is equal to a negative 7.29. Right? Because at that point, they're basically the same line when you zoom in, right? When you zoom in on this point, the curve looks a lot like the budget line. So they're parallel, right, at that point. Now, as you move up along the indifference curve, as you move up along it, what's happened to the marginal rate of substitution? What's happened to the slope? It's getting increasingly negative. Meanwhile, utility is 216 here. Utility is 216 here. Utility is 216 here. So utility is remaining constant along this indifference curve. So utility remains constant, but the MRS is getting increasingly negative, right? As you move up and to the left along it, right? Now, the reservation wage is the slope at this point. And the reason why that is because if the wage goes up a little bit, then the person is no longer indifferent between work and not working. At this point, the person's indifferent, just indifferent between working and not working, right? So the wage goes up a little bit, it'll probably trigger that person to start working. So we're calling the wage at that point the reservation wage. And that's because, again, the worker will work if offered a wage exceeding that rate, right? Exceeding 729. And we're going to see that here. Suppose employers raise wages by $22.76, right? So down here, I'm gonna add 22.76, right? So I get a new wage of $30.05. Okay, so $30.05. Okay, now what's that going to do to our line up here? This line is pretty flat here because it was only 7.29, right? When the wage goes to $30.05, it's going to be much steeper, right? So the line is going to steepen. It's not going to flatten the budget line. It's going to steepen the budget line, right? And that's exactly what happens, right? And we get a new optimal solution. The new budget line is just tangent to this third indifference curve that represents utility equaling 272 at every point along this green curve, right? So we get a new budget line here. We get a new budget line. C equal 2987 minus 30.05. Why is this 29.87? Well, look, we have the new wage of 30.05. We're multiplying that new wage by 80, the amount budgeted for leisure or labor. And then our allowance is held constant at 583, ceteris paribus. So the intercept here is this 2987. And this is the slope, which, if you remember, the slope of our budget line, is the wage. So the original wage was $7.29. The new wage is $30.05, right? This results in the new optimal solution that is on the new budget line. As I mentioned earlier, the new optimal solution is right here, right? And that makes sense because if we hold leisure constant and come down to this indifference curve, right? We have less consumption. So for the same amount of leisure, we have less consumption. So obviously this point is going to have lower utility than that point. And then if we do the same thing, if we hold consumption constant along this dashed line, but we reduce leisure, then obviously we're going to have less utility here, right? Because we have less utility, but the same amount of consumption as we do here, right? So this curve and this curve represents lower levels of utility. If I draw a fourth indifference curve out here, well, on the red budget line, because it doesn't intersect the red budget line, any point on an indifference curve beyond this red dot is unattainable. We're assuming there's no credit. There's no credit cards here, no debt, right? We can only consume our income, right? So our optimal solution is on the new budget line that is just tangent to the indifference curve. Now, there are infinite many indifference curves, and we're only showing you 3 of them, right? We're only showing you 3 of them. So higher worker utility, right? So we're at this point here, and our utility is now 272, not 216. So we have higher utility, right? Okay. And our leisure level is 49.7. 49.7. So I'm going to change my leisure here to 49.7. Okay. Now, if I'm consuming $49.70 in leisure, right? Then I'm supplying 30.3 hours in labor, right? I'm supplying 30.3 hours in labor each week. Because 49.7 minus 80 is going to be 30.3. So this number and this number adds up to 80 because there's a total of 80 hours devoted to leisure and labor, right? Now, this is going to result in that higher level of utility, right? The higher level utility in my model is 272. And we're going to use the red consumption function, right? The new consumption function, the red one, the red consumption function is over here, right? This is 2987. This is $30.55. Leisure is 49.7. So I got 49.7 times a wage of 30.05. And then I'm going to subtract that from this new intercept, 2987. Or I can calculate it down here, right? The allowance is 583. The new wage is $30.05. And then we're working $30 or 3 hours and 30.3 hours a week, right? So when I use the income approach to calculating the amount of consumption this person makes versus calculating the consumption function from the budget line, I get the same exact numbers, right? All right. So $1,493.51. When the hourly wage was initially equal to, what was it initially equal to? $7.29. Hours worked was what? Hours worked was 0, right? So at the initial wage, the slope of the black line, hours worked was 0 because leisure was 80, right? Leisure was 80. At the new wage of $30.05, which is right here, right? Weekly hours worked rose to what? The person works now $30.3 hours per week. 30.3 hours per week. Right. Now down here, I'm gonna do a fraction. I got the change in the wage divided by the change in hours worked. Right? The wage was $7.29. The wage now is $30.05, right? So I'm taking the difference of these two, right? This is what it was, and this is what it is, right? So this is minus was, and the is and was are the hourly wages before and after, right? Now, at $7.29 per hour, the person worked 0 hours, right? At $30.05, the person works 30.3 hours, right? And the slope is the rise over the run, right? The rise is the change in wage over the change in hours worked, right? So in order to find out what this equals, I'm going to delete the left-hand side. And my slope is 0.75. Whoops. $30.05. Yeah, the new wage is 30.05. I typed it wrong box. So my slope is 0.751. The slope of my labor supply equation. So we're building a labor supply equation here, right? So the labor supply equation has W on the left, wage equals some intercept. Just call it intercept, plus some slope times hours worked, right? Well, the slope, we just calculated it. The slope is what? Slope is 0.751. Okay, so the slope is 0.751. So this value here, this beta, that's 0.751, 0.751. Now we call this the point slope equation because this beta is the slope and this W0, H0 is a point, right? And so the initial wage was $7.29 and the initial hours worked were 0, right? We're going to let this H be free and this wage be free, right? The slope of our line here, the change in hours worked, the change in wages over the change in hours worked, that's our slope of our labor supply equation. And the slope of the labor supply equation, the beta, is 0.751. Hmm. Hmm. Okay. Now let's double check to make sure this labor supply equation works. So our wage is equal to 0.751 times H plus 7.29. Notice with H equal to 30.3, the hourly wage is 30.05 if we round to 2 decimal places, right? So we get this wage rate from our labor supply equation when we plug in hours worked of 30.3, right? What about the other one? What about when the wage is 7.29? Sorry, when hours worked, where's hours worked? Okay, so when hours worked is 0, right? When hours worked is 0, leisure is 80. So leisure is 80, hours worked is 0. And so this is 0, and 0 times that slope is 0. So the wage rate equals 7.29. So we just verified that that this equation is our labor, the consumers, the workers' labor supply equation. It's upward sloping, right? We're going to use the midpoint formula to compute the percent change in the wage. The midpoint formula let's do this. We got the percent change in the wage, and we got the percent change in hours worked, right? Use the midpoint formula. So we need the percent change in wages. We need the percent change in wages and the percent change in hours, right? The percent change in wage is equal to the difference in the wage, right? The difference in the wage divided by the average of the two wages, right? So we got wage 0 plus wage 2 divided by 2, right? We want the average. So we have to average the two wages, right? Sorry. We got the initial wage, we'll call it the first wage. The first wage plus the second wage divided by 2, that's the average. That's the midpoint, right? So that's how we calculate and this is just the change, right? This right here is just the change. So we got W1 minus W2, right? So that's percent change in wage using the midpoint formula. So let's go down here. So this right here is the change in the wage, right? That's the change in the wage. So we were at 7.29, now we're at 30.5. So that's the change in the wage. And then we need to calculate the average. Okay, so we're going to add the two together, and we're going to divide by 2, right? So down here is the average wage, the midpoint of the two wages. And that's the change in the wage. So the percent change in the wages using the midpoint formula is 1.219. Okay, I had to change it to percent change, right? So I have to multiply all this stuff on the left by 100 to convert it to a percent. So I need to change this to 121.907. Okay, now it's in percentages, right? Now we need to do the same for the hours worked. So we're going to do a fraction and then a fraction. We're going to do the difference. And then we're going to do we're going to add them together. And we're going to divide by 2. So hours worked was initially 0, right? Hours worked was initially 0. And then hours worked ended up where? At the new wage of 30.05, the worker chose that much leisure and that much work. So work went from 0 to 30.3. So I'm going to calculate the percent change in hours worked by using the midpoint formula, which means we have to add the 30.3 to what the hours worked were initially. And this will give us the average right here, right? That right there is the average. We're going to multiply that all by 100% to convert it to a percent. So when the wage went up by 121.907%, hours worked increased by 200%. We're going to take the ratio of these two numbers to compute the worker's wage elasticity of labor supply. So I'm going to dig in and do a fraction. The 121.097 is the percent change in the wage. And 200% is the percent change in hours worked. And it looks like our workers' wage elasticity of labor supply is 0.60, well, 10, right? Okay, so we got to remember the elasticity formula. The elasticity formula for demand elasticity or supply elasticity is a percent change in quantity. Percent change in quantity here is the hours worked, right? And then down here's the percent change in the price. And here the price is the wage rate, right? Okay, so the percent change in hours worked, that was, we went from 0 to 30.3 hours of work. So that's 200 up here, right? And then the percent change in the wage, we went from 7.29 up to 30.05, and the midpoint percent change is 121.907. Right? So that ratio is the elasticity. So I got to flip these down here. So the elasticity of labor supply is 1.641. Okay, 1.641, right? The wage elasticity of labor supply implies that each 1% increase. So I'm going to rewrite this as I should have DW. This should be DH. Okay. And the elasticity equals a single number, 1.641, right? The elasticity is a two-part thing. This percent change in hours worked over the percent change in wages, right? But it equals one thing, right? One number. I'm going to decompose it into its components. In the numerator up here, we have 1.641. In the denominator down here, we're going to put a 1. Right? And both of these are positive, right? Both are positive. Okay, so what this says is a 1% increase in the wage, right? This is the percent change in the wage. Because this is positive, you could say a 1% increase in the wage results in a 1.641% increase in hours worked. So this 1.641 ends up going right here. So the person's labor supply equation, if I open up new Desmos, if I open up new Desmos and I want to graph labor supply, I do so with W on the y-axis, the vertical axis, and H on the horizontal axis. It equals 0.751 H plus 7.29. So this red line would be that person's labor supply equation. And as the wage rises, this person generally works more. Okay.